Hi guys, and welcome to Basic Integration Rules. This is section 7.1 in our textbook. So the first thing that I want us to talk about is just what is the essential question of this lesson? So our essential question is, how do you identify the proper integration rule for a given integrand? And if you look over here on the left side of the screen, we have 20 basic integration rules. Now, I would recommend pausing the video here and writing these down or printing these out. You are going to want to have these rules in front of you throughout this entire video. You don't have a lot of these memorized, and that's okay. You don't have to have them memorized because you do have this table. About the first half you should have memorized, and then after that it's a matter of using the rule and applying it. But you want to be able to recognize these. So on this side, it's saying the antiderivative of k times f of u du equals k times the antiderivative of f of u du. And this is what we just call our constant multiple rule. And so if you have a constant multiple, you can always put that outside the integral or inside the integral. This is when you have two different functions, either adding or subtracting, you can split them up. So the antiderivative of f of u plus or minus g of u du is the same thing as breaking this into two separate integrals. This is the integral of a constant. The integral of a constant, or the antiderivative of a constant, is u plus c. This is our basic power rule. And so our power rule says that you have u to the nth power du, and so the antiderivative of that is u to increase the power by 1 and divide by that new power plus c. This one is our log rule. And so if you have a function in the denominator and its derivative is in the numerator, you can apply this log rule. This is our e to the u. This one I don't know if we have memorized, but up until 6 we have them memorized. We have 8 and 9 memorized. And then beyond that, you're going to want to have this table in front of you. So let's go ahead and do some examples here. So example 1 is a comparison of 3 similar integrals. And actually in this, I would like you to pause the video and see if you can work these out, just tapping into the things that you already know. And remember, keep that integral table in front of you. So keep the review of basic integrals by your side, pause the video here, and attempt to work out these 3 examples. Make special note of the rules and techniques you used to find each integral. And so the 3 integrals that I want you to try out are: find the antiderivative of 4 over x squared plus 9 dx, find the antiderivative of 4x over x squared plus 9 dx, and then find the antiderivative of 4x squared over x squared plus 9 dx. So go ahead and pause the video here and see what you can do. All right, I am hoping that you paused the video and you attempted those 3 problems. And now I'm going to work through A, B, and C with you. So example 1A was the antiderivative, find the antiderivative, I guess, of 4 over x squared plus 9 dx. Well, the first thing that I notice is I have this 4. Let's see if I can get my pen to work here. Sometimes it works better than other times. So I have this 4 right here. Guess I should turn on the pen. Oh, now it's on. This 4 is a constant multiple. And so I'm going to pull that 4 out in the front. And that's going to give me 4 times the integral of 1 over x squared plus 9 dx. So that is going to look like this here. Now I'm going to look at my integral table of all of those rules, and I'm going to see, does this look like a rule? And one thing that I notice is that I have something squared plus something squared, in my denominator, that 9 is actually the same thing as, so we've got x squared plus 3 squared. So I have something squared plus something squared. Is there a rule in our table that pertains to that? There is. If you look at rule 19, we have some number squared plus some function squared, and that antiderivative would be, or not the antiderivative, I'm sorry, the derivative of u would be in our numerator. And that is going to be our arctangent rule. So the next thing that we're going to do is we're going to rewrite the equation to help us see that basic integral rule, which we've actually already done. So this helps us see, this would be our u. This is u because that is an equation. So your u is always going to be whatever one includes the variable. And this is a. And because it's a plus sign, it doesn't matter what order these go in. So it's okay to have u squared plus a squared. So we want to identify a and u, which we just did. A is going to be 3, and u is going to be x. So we can rewrite this as 4 times the integral of 1 over u squared plus a squared dx, knowing that u is x. So if I replaced u with x and if I replaced a with 3, then we'd get exactly the same thing as above. Now we can apply this rule. So the derivative here, and we want to make sure, is du really on the top? So if u is x, then du is 1. And we do have 1 on the top. And so this rule does work because we have du in our numerator. And then we have a squared plus u squared in our denominator. And this dx is actually a part of du. So we're going to apply this arctangent rule. And what it says is that when we take the integral of du over a squared plus u squared, we get 1 over a times arctangent of a of u over a plus c. And that's what we see here. And you will notice that that 4 is still out front. That 4 is still out front. We can't ignore that 4. And so we have 1 over a arctangent of u over a plus c. And all we had to do was apply that rule. Now, of course, there's one more step, and we need to substitute those values of u and a back into the function. So all of the a's turn into 3's, and all of the u's turn into x's. And this is the antiderivative. 4 over 3 arctangent x over 3 plus c. Is that what you got? If it's not, that's okay. We're learning this right now. All right, let's look at example B. So B gave us 4x over x squared plus 9 dx. And this is what I see. I see that x squared plus 9 in my denominator. And you know what? Before we learned something called u substitution. And using u substitution, we had to find a function. And then if we could also find its derivative, then we could do some u substitution here. And what I see is I see that if I were to assign u to be x squared plus 9, the derivative of that du would be 2x, because the derivative of 9 is 0. Which means that if I could make sure that I had a 2x in here somewhere, I could use u substitution. Well, I have a 4x. Let's pull a 2 out of that 4x. And so this would look like 2 times the integral of 2x over x squared plus 9 dx. And again, that's our constant multiple rule. I think that this is going to get covered up, so I'm going to erase it for just a moment and it'll pop back up. Don't worry. but I just wanted to show you where I was getting these things from. So that was the constant multiple rule, and we get this. We get 2 times the integral of 2x over x squared plus 9 dx. And then this is a problem that we've done over and over again. We've seen things like this. This is just u substitution. So we need to determine u and du, which we have done, which means that I can rewrite this piece of it as a du, and that's in the numerator, and I can write this part of it as u. So this is the same thing as 2 times the integral of du over u. Now we need to integrate. Well, what rule are we going to use here? Hmm, hmm, hmm. Hmm. Well, we can look at our table, and if you look at rule number 5, this is our log rule. This is the log rule that we're going to use. And so the log rule says, essentially it says if you are taking the integral of 1 over u times du, it's going to be ln of u plus c. Well, here we go. This is going to be 2 times ln of u plus c. And you know what we need to do. We have to replace the u. We have to replace the u, and so that u is what we already identified up here. We have to plug that back in for u. So we get 2 times ln of the absolute value of x squared plus 9 plus c. That wasn't so bad. Now, this is the final answer. So this final answer is perfectly acceptable, but let's practice. Let's practice breaking up our ln's, and let's see if we can rewrite that. No, I changed my mind. Let's keep it like this. All right. So c was the next one, and we have 4x squared over x squared plus 9 dx. So we want to find the integral of this here. Well, I'm thinking because the degree of the numerator is the same as the denominator, I should use division to rewrite an improper rational function as the sum of a polynomial and a proper rational function. What? What? Let's long divide it. Let's long divide this. Okay, so long division, it has been a long time since we did that. So let's put x squared plus, nope, nope. I forgot how to long divide. Oh no. Like I said, it's been a long time since we've long divided, huh? All right, so let's put our, the thing that we are dividing inside, so 4x squared, and then we will put our divisor on the outside. And if you remember long division, you take just this first term, and you are going to see how many times this goes into this. And then you will line up your like terms. So x squared goes into 4x squared 4 times. And then, um, we multiply. So 4 times x squared is 4x squared times 9 is 32. And then we subtract. And so we get 4x squared minus 4x squared is 0. 0 minus 32 is a negative 32. And that's our remainder. And so we write our remainder up on the top like minus 32 over x squared plus 9. Okay, so we can rewrite this integral as the integral of 4 minus 32 over x squared plus 9 dx. Then we can break this into two integrals because of that minus sign. So we have the integral of 4 dx minus 32 1 over x squared plus 9 dx. We can integrate this by increasing by an exponent and then dividing by that exponent. So this becomes 4x. And then this, we're going to look at our integral table. We're going to look at our integral table. So go ahead, look at your integral table and see what looks like a function squared plus, this is another perfect square, plus a squared. And while you're looking at your integral table, I'm going to erase this mess I have and put it a little bit prettier on here. So hopefully you're looking at your integral table right now and you're trying to figure out which one looks like that. And hopefully you got rule 19. So rule 19 is our arctangent rule. And our arctangent rule says that if we have du over a squared plus u squared, the antiderivative of that is 1 over a arctangent u over a plus c. And we actually use this arctangent rule in example A. So we already know how to identify a and u. So our a is 3 and our u is x, which means then we could apply that arctangent rule. So we integrated this already, and then we got 36 times 1 over 3 because a was 3, arctangent x over 3 plus c. We're going to simplify next, distribute in that 36 right here. 36 divided by 3 is 12. And so we get 4x minus 12 arctangent of x over 3 plus c. All right. So if you didn't get those right your first time through, that's okay. That's what this is all about. We have to practice, practice, practice to make perfect. So I now have, oh, not yet. I have a few words first. So oftentimes you tend to overthink simple integration problems. Remember to consider basic integration rules first and then use more complex strategies if needed. For example, in that last one that we did, the integral for part 1 for A, you could just use the arctangent rule. But in C, we had to rewrite it first and then use the arctangent rule. So always keep this table in front of you for this lesson and maybe for the upcoming lessons as well, so that you can refer back to it. And that is going to make math much easier. All right, so now what I have is something I want you to practice on your own. And so you're going to need to pause the video, attempt to work out these 3 examples, and make special note of the rules and techniques you used to find each integral. And then as soon as you hit play, the answers are going to pop up. So I'm not actually going to work these ones out with you. In our Q&A session, we can go over any of these that you would like. Just make sure you make special note of them. But go ahead and pause the video and work out these 3 examples. Okay, so hopefully you had enough time to pause the video. Hopefully you worked these out. Now I'm going to put the 3 answers up on here. And again, I'm not going to work these out, but if you have specific questions, write them down. We'll do them in our Q&A. So the first one is 2 arc sine of x plus c. The second one is negative 2 times the square root of 1 minus x squared plus c. And the last one is negative ln of the absolute value of 1 minus x squared plus c. Alrighty. Let's do another example. So in this example, we're going to use two basic rules to solve a single integral. And here is our integral. Evaluate the integral from 0 to 1 of x plus 3 over the square root of x minus x squared dx. The first thing that we should do is we should write this as two separate integrals. So we have that plus sign in between, so we can break this apart with that plus sign. And so what that's going to look like is we are going to have the integral from 0 to 1 of x over the square root of 4 minus x squared plus the integral from 0 to 1 of 3 over the square root of 4 minus x squared. And of course, both of these are with a dx. This one here, the very first thing that I started thinking about was u substitution, because look at this. That's x squared. The derivative of x squared is 2x. I have almost that on the top. I might have to do some adjusting, but I have almost that on the top. This one here, I'm thinking maybe we should move the 3 out, and then I should look at my integral table. And looking at my my chart of integrals, maybe I can find something that's going to work with that. So the first thing that we got to do, we got to rewrite this as two integrals, which we just did. And then we want to look at our integral tables to see if anything is going to work. And look at this. Rule 18 is the arcsine rule. So let's use the power rule and the arcsine rule. So this first piece here, let's say that u is 4 minus x squared, which then makes du negative 2x. And negative 2x, we have a negative 2 missing here. So if I add a negative 2 here, I can add a negative 1/2 here to counter it. So negative 1/2 times negative 2 is positive 1, and therefore I did not alter this at all. That's nice because this is then my du, and this whole thing here is my u. So that allows me to solve this out, saying negative 1/2 times du over the square root of u, which that's the same thing as negative 1/2 times u to the negative 1/2 du. And then I can integrate this by increasing by one exponent. So increasing by 1, this becomes positive 1/2 because negative 1/2 plus 1 is positive 1/2. And then you divide by positive 1/2, which is the same thing as multiplying by 2. So that's going to be the power rule piece of it. This piece of it, as we can see, is going to be the arcsine rule. And so this piece of it, I'm going to pull that 3 out. I'm going to go from 0 to 1, and then this is going to be the square root of 2 squared minus x squared. So a is 2 and u is x. So this integral becomes 3 times the arcsine of x over 2 plus c. Not plus c, because we are actually integrating from 0 to 1. Okay, so let me erase that so that we can see this better. Okay. So this is what we just did. I can't find my cursor. Where is it at? Oops. I don't know how to undo that. Okay, so this is what we just did. It's a little bit uglier, but this is going to be the power rule, and then this is going to be our arcsine rule. And so we get negative 4 minus x squared to the 1/2 plus 3 arcsine to x over 2. And then we need to evaluate it. So to evaluate it, we're going to plug in the 1 and we're going to plug in the 0. So we'll plug in a 1 here. So we have negative 4 minus 1 to the power of 1/2. So that ends up being negative root 3 plus 3 times arcsine. Plug in a 1 of 1/2. Well, the arcsine of 1/2 should be pi over 6. And then when you plug 0 in, we'll get 2 and 0. So we have this here. So negative root 3 plus pi over 2 minus negative 2 plus 0. Let's go ahead and plug that in the calculator and get what the actual answer is. I don't know how to hit play. Oops. I don't know how to make the pen go away. I don't know why technology is so hard. Okay, well, I don't know how to make that work. Hopefully you plugged into your own calculator and you got approximately 1.839. All right, so here's a practice for you to try on your own. Pause the video, work this problem out on your own, and when you resume the video, the answer will appear. Good luck. So here is your equation that I'd like you to work out. Find the integral from 0 to 4 of x minus 7 over x squared plus 16 dx. Go ahead and pause the video here, and when you resume the video, the answer will appear. Okay, hopefully you had enough time to work out that problem. And so the answer is 1/2 ln of 2 minus 7 pi over 16, which is approximately negative 1.028. So if you still got that negative 1.028 and you didn't get this piece of it, chances are we just did it a different way, which is okay. All right, let's try let's talk about a few things, I guess. So rules 18, 19, and 20 of the basic integration rules have expressions involving sums or differences of two squares. We talk about sum and difference of squares all the time. And so if you see anything like that, where you have a constant that's a perfect square, and then you have an equation that's squared, whether it's x or a different variable or even a set, a binomial, these expressions are often apparent after using U substitution. So anytime you see one of these, think that possibly you're going to be using rules 18, 19, or 20, which is the arcsine, arctangent, or arcsecant rule. All right, so in this example, we are going to do a substitution involving one of those difference of squares, so a squared minus u squared. And being able to recognize it and being able to pick one of the rules 18, 19, or 20 is going to be super helpful. So we're going to find the integral of x squared over the square root of 16 minus x to the 6th power dx. Now, this might be a little bit tricky because you're thinking 16 is a perfect square, but x to the 6th power isn't a perfect square. But it actually is if you rewrite it. So because the radical in the denominator can be written in the form of the square root of x squared minus u squared, we get 4 squared minus x cubed squared. We can actually use the substitution where u is x cubed and du is 3x squared. Because when you remember, if you take the derivative of x cubed, then you get 3x squared. So let's work it out. We're going to rewrite the integral, and our integral that started out as x squared over the square root of 16 minus x to the 6th dx is now going to be 1/3 times the integral of 3x squared, because we had to include this 3. This 3 wasn't originally there, right? And so the only way to put the 3 there is to counter it with the 1/3, because 1/3 times 3 is 1. So we didn't alter anything. And then we rewrote our denominator as 4 squared minus x cubed squared all underneath the radical, because this is equivalent to this, but now it's in the form where we can use Rule 18. So Rule 18 is our arc sine rule. And now taking the derivative of this, or not the derivative, I'm so sorry, the integral of this, finding the antiderivative, is really simple because we have du in our numerator, and we have the square root of a squared minus u squared in our denominator. And so really, it's going to be 1/3 times arc sine of x cubed over 4 plus c. So let's see how this plays out. We're going to substitute in x cubed for u, and that makes this our du. And so we get 1/3 times the integral of du over the square root of 4 squared minus u squared. We're going to use our arc sine rule, and we get 1/3 times the arc sine of u over 4 plus c. And then we are going to rewrite as a function of x. So we get 1/3 arc sine of x cubed over 4 plus c. So as soon as you recognize the difference or the sum of squares, it's going to become a lot easier to then just apply one of those rules. So let's give you a practice to do on your own. So just like the previous one, pause the video and work this problem out on your own. When you resume the video, the answer will appear. So I'm not going to work out the answer for this, but if you have a question on it, then please write it down, and during our Q&A, we will answer it. So go ahead and pause the video here and work this out. Okay, hopefully you had enough time. And you're resuming this video because you have finished. The answer to this one is 1/4 arc secant of x squared over 2 plus c. All right, the most commonly overlooked integration rules are actually the log rule and the power rule. So in the next two examples, we're going to work through the log rule and the power rule, and they're going to be disguised. So the log rule and the power rule, before school got canceled, those were our favorite rules. They'll still be our favorite rules. We just have to do some manipulation to make them look the way we want. All right, so example 4, this is going to be a disguised form of the log rule. And so we're going to find the integral of 1 over 1 plus e to the x dx. And guys, when I first started working out this problem, I was thinking, oh, how in the world am I going to do this? And I actually took sidewalk chalk and I worked this out with some sidewalk chalk. So the integral does not appear to fit, that should say 1, one of the basic rules. The quotient form, however, suggests the log rule because it's in this form here. We're thinking, I want to use a log rule. So if you let u be 1 plus e to the x, then we know that du has to be e to the x dx. We don't have an e to the x dx in the numerator. However, if we add and subtract e to the x to the numerator, you're not adding anything new, you're keeping it the same, but that allows us, adding and subtracting the same thing is the same thing as adding 0. That allows us to have an e to the x in the numerator. Say what? What does that look like? Like this. So the integral of 1 over 1 plus e to the x dx is the same thing as 1 plus e to the x minus e to the x, because plus e to the x minus e to the x is 0. I have not added anything to this. So let's rewrite this. Let's rewrite this. We have 1 plus e to the x over 1 plus e to the x because I took this piece of it. Why do you think I took that piece of it? When I divide that, what does it equal? You're right, 1 minus e to the x over 1 plus e to the x dx. This is really freaking cool because look at this piece here. This equals 1, and this equals, well, we don't know yet. So let's rewrite it as our two integrals. We're going to have the integral of 1, or dx, minus the integral of e to the x over 1 plus e to the x dx. And this we now can do u substitution on. Look at this. This guy right here. If we say u is 1 plus e to the x, that means du is e to the x dx, which means that this bad boy here is the integral of du over u, which is ln of u. What? What? This is crazy. So the integral of dx is just x, and then the integral of this is going to be negative ln of u was 1 plus e to the x plus c. So when we rewrote this, we were able to use just the simple log rule, and we love the log rule, but we did have to do some crazy manipulation up here ahead of time. And as long as you're adding or subtracting 0, you're allowed to do that, just like we're allowed to multiply or divide by 1. All right, let's do a disguised form of the power rule. So we want to find the integral of cotangent of x times ln of sine of x dx. What? That looks disgusting. Okay, so again, this integral does not appear to fit any of the basic rules. But we have two primary choices for u. We can either say u is cotangent of x, or we can say u is ln of sine of x. Well, of the two, the second choice is the appropriate one, because if this right here is u, what does that make du? If u is ln of sine of x, that makes du cosine of x over sine of x. Because remember, the derivative of ln of x is 1 over x. So the derivative of ln of u would be du over u. Here's our du, here's our u. That's the derivative of ln. So if you forgot the derivative, where's my pen at? The derivative of ln of u, oops, is du over u. Here's our u, and our du would be cosine of x. And that is just cotangent of x dx, which means, oh my gosh, this is insane. Which means that this integral right here, we could rewrite it as the integral of u times du. What? What? Now we can use the power rule. So using the power rule, you're going to increase by one exponent and divide by that exponent. So we get u squared over 2 plus c. And now we just need to substitute back in our u. And so we get 1/2 ln of sine of x squared plus c. Easy as pie. All right, so now I would like you guys to practice a couple of examples on your own. So just like the previous ones, pause the video and work this problem out on your own. When you resume the video, the answer will appear. Good luck. Again, I am not going to work out these answers, and so if you need me to go over them during our Q&A, please make special note. So pause the video here and work through these examples. Okay, hopefully you had enough time to work through these questions, and so the answers are 1/4 arc secant of x squared over 2 plus c, and 1/3 e to the negative 3 cosine of x plus c. All right, the last example that we're going to do is going to tie into our trig identities. And so you learn these trig identities in pre-calculus. No, you don't have to have every single one of them memorized, but if you do have this sheet in front of you, it would be good. The ones that you want to have memorized are the reciprocal identities, the Pythagorean identities for sure, the quotient identities, and then you want to be able to recognize that there is a double angle identity and there is a half angle identity. You want to be able to recognize that, and then from there, obviously, you could look up what did that actually equal. So trig identities can often be used to fit integrals to one of the basic integration rules. So sometimes you're going to be given something and you're like, well, crap, this isn't on my list of rules, but you can manipulate it using a trig identity so that it does fit those rules. So let's do a practice with that now. So this is going to be example 6, use trigonomic identities. And we are going to find the integral of tangent squared of 2x dx. Now, the first thing you might be thinking, well, hopefully you are, you're going back to your list and you're looking at that list and you're thinking, this is not on my list. I don't have a tangent squared of u on my list. However, there is a secant squared of u. And so we could use the Pythagorean identity to rewrite this. So the Pythagorean identity that's in question here would be the tangent one. So if you look right here, we have tangent squared of theta plus 1 equals secant squared of theta. So tangent squared of theta plus 1 equals secant squared of theta. If I wanted to get tangent squared alone, I could subtract 1 from both sides. And so tangent squared of theta equals secant squared of theta minus 1, which means that I could replace the tangent squared piece of it if this was tangent squared of u, meaning that u is 2x. So let's work through this problem then. So we're going to substitute u as 2x, and so that means our integral is going to look like this. It used to be the integral of tangent squared of 2x dx, and now it's going to be 1/2 tangent squared of u du. Where did that 1/2 come from? Oh yeah, du is 2 dx. We didn't have a 2 out front before. And so by putting a 2 here, we have to put a 1/2 here. Now the 2 and the dx become our du. Okay, so now we can replace this with the trig identity. Tangent squared of u is the same thing as secant squared of u minus 1. So now we have 1/2 times the integral of secant squared of u minus 1 du. And now we can rewrite as two integrals. So we're going to have 1/2 times the integral of secant of u du minus 1/2 the integral of du. And now we can use the rule from our integral table. Number 14 says the integral of secant squared of u du is tangent of u. That should say plus c. Plus c, put a plus there. So plus c. And so the integral of this, it's going to be 1/2 tangent, well, u is 2x, so tangent of 2x. And then the integral of this, you increase by one exponent and you divide, so this becomes 1/2 u. So we have 1/2 tangent of u minus u over 2 plus c, and then we have to replace our u, which is 2x. And so we have 1/2 tangent of 2x minus x plus c. You might be asking, how the heck did that just turn into an x? Well, when we plug in 2x here, 2x over 2, the 2's cancel out and you're left with just x. So by substituting in our Pythagorean identity, we were able to solve this. So let's do one for you to practice. So just like all the other ones, pause the video, work this problem out on your own, and when you resume the video, the answer will appear. So you're going to find the integral of sine of 2x dx. Because it's squared, I would think about looking at one of those Pythagorean identities. That's not your only option, though, of course. Okay, so hopefully you had some time to work that out, and um, we we get the answer to be x over 2 minus 1/4 sine of 2x plus c. All right, and so our final words for this section are here are some procedures for fitting integrands to basic integration rules. So you've got expand, separate, complete the square, divide in proper fractions, add and subtract terms in the numerator, use trig identities, and multiply and divide by the Pythagorean conjugate. So in our examples, we did a lot of these. We did a separate the numerator. We did divide improper rational functions. We did add and subtract terms in the numerator, and we did trig identities. Um, the three that we did not do are things that we have done over and over and over again, and that's expand the numerator, separate the numerator, and multiply and divide by the Pythagorean conjugate. So as you're working through these, there are 20 basic rules to look to, which is a lot. So keep those rules in front of you and see if you can manipulate the problem to look like any one of those rules. And I think that is what is going to help you the most.